In today's lecture, we are going to discuss about photoelectric effect. As the name suggests, photo means the light, electricity, we all know that. Basically, we are going to observe the light electric effect due to the photon that we incident upon the metallic surface. And the following terms we are going to discuss about in this lecture: threshold frequency, saturation threshold frequency, saturation current, stopping potential. And here the experimental setup, as you can see, it is simply containing the vacuum chamber, a metallic surface on which the incident light incident light will drop, and the electron from the metallic surface will be ejected, and it will be attracted by the detector which have the positive potential, and we complete the circuit, and we will measure the current simply. My next question is simply that any frequency of the light that we are going to incident on the metallic surface will uh, will emit the electrons. Yeah, we have to provide a certain minimum threshold frequency, so that the electron from the metallic surface can eject. So answer is that we have to provide the minimum threshold frequency so that the electrons will eject from the metallic surface. The minimum threshold frequency, here we have shown the threshold frequency that we require to eject the electron from the metal surface, and above which above which and below the frequency of the threshold frequency, it will not eject the electrons. They remain in the bound state in the metal surface only. So you have to provide a minimum threshold frequency. We all know that the relation of the energy and the frequency. Here the mu is the frequency and the h is the Planck constant. And simply it says that if we increase the frequency of the incident beam, and the energy of the beam will increase, isn't it? So simply if we have a metallic plate, simply if we incident the frequency of h mu, let us suppose that it is greater than the threshold frequency. I am showing the threshold frequency by V naught. Then electron from the metallic surface will eject out, and this electron, how much energy it contain? It is simply the conservation of energy law. Here we have stated that the frequency of the incident beam, and here the minimum threshold energy uh, that is required to eject the electron, just eject the electron from the metal surface, and the rest of the energy is going to impart to the electron, impart the kinetic energy to the electron. That is, here we have shown that if the incident frequency of the incident beam will increase, the kinetic energy of the photon, kinetic energy of the electron will increase. Uh, Kinetic energy, and here the threshold uh, threshold energy that is required to eject the electron from the metal surface. to the next slide. Effect of the intensity of the light. Intensity is the number of photon, intensity of the light, the number of photon per unit area per unit time. If we increase the intensity, means the number of electrons are increasing per unit time per unit area. Okay. Then so it is simply saying that if we increase the intensity of the light, then the photoelectric current will increase. Means the number of electron ejected from the metal surface will increase. Here I point out that the kinetic energy of the electrons beams will not increase. It is simply saying that if we increase the intensity means the number of electrons uh, number of photons we are increasing on the uh, metallic surface, then the number of ejected electrons will increase. Number of ejected electrons will increase. Not their kinetic energy will going to decrease or increase. Uh, we have roughly estimate that if we if we incident a one photon which is greater than the threshold frequency, it going to eject the one electron. There is higher probability to eject a one photon. If let us suppose that if a surface have a uh, threshold frequency of 2 electron volt, if we provide the four if we provide the energy of 4 electron volt, is that mean it the photon will one single photon will eject the 2 electrons? No. Basically, one electron will eject the one single electron from the metal surface, and the rest of the two rest energy, the required energy, threshold energy is 2 electron volt. That will impart to the that will just impart to the electron and come to the surface, and the rest to electron volt energy will impart a kinetic energy to the kinetic energy. This is 2 electron volt will with the kinetic energy of the electron that ejected from the metallic surface. Effect of the potential applied. Let us suppose that we are providing a certain intensity. We are providing a certain intensity. Let us suppose I1. Uh, if we and the threshold frequency, the frequency of the incident beam is greater than the threshold frequency. So we till now we have some idea that the if the it is if the incident frequency of the light beams is greater than the threshold, that the remaining energy will impart the kinetic energy to the electron, will give the rest of the energy will given to the as a kinetic energy of the electron. So if we are increasing the intensity, means the number of electron are increasing, number of electron are increasing, so their kinetic energy are also equal. Kinetic energy of the electrons are also equal because we are not going to change their frequency. So here is the point that first of all, I define the stopping potential. The stopping potential is nothing but the minimum potential required to stop the electrons to come to the detector plate. The minimum potential. So if you are increasing the intensity, number of electrons are increasing, not their kinetic energy. So so there so we have a one potential for the different intensities. Let us consider that we we are providing the we are providing we are providing here the retarded potential, and then simply the metallic surface on which the incident beam are increasing. Here the re stopping potential, the here we all know that the electron will come out from the plate in this direction if it is positive plate, and then the minimum potential that is required to stop the electron not to reach at the detector plate. If we are increasing the intensity, means number of electron are increasing, not their kinetic energy. So we have to provide the stopping potential for all these waves are should be equal, means at a fixed point. That's all. And in the next illustration, effect of the frequency of the incident radiation on the stopping potential. Here we are going to increase, we are taking the frequencies in this order. V3 is greater than V2 and V3. If the frequency is increasing of the incident photon, we are simply saying that the electron ejected from the metallic surface have the more kinetic energy. So we have to provide the retarded potential in the opposite direction to stop to the electron to not come to the detector plate. So if the frequency is greater, we have to provide more retarded potential so that it not come to the detector plate. So here we have illustrated. Here is the saturation current. The current will if we increase the frequency, it doesn't mean that it will increase the number of electrons. Kinetic energy will be increased. Note there, number of electrons will be same. That's the, that's the point. And the graphical result, we have already seen that the stopping potential V naught varies linearly with the incident frequency, incident radiation for a given photosensitive material. For a given photosensitive material, the stopping potential varies linearly with the frequency of the incident radiation. And second point is there is a certain minimum cutoff frequency for which the stopping potential is zero. And these observations have the two implications. The maximum kinetic energy of the photoelectrons varies linearly with the frequency of the incident radiation, but is independent on its intensity. We have seen that. For a frequency mu of the incident radiation lower than the cutoff frequency, no photon emission is possible even if the intensity is large. If you are increasing the intensity, means the number of photon you are increasing on the metallic surface, they are not going to eject the electrons if you are if you are if you are providing the frequency which is less than the threshold frequency. So at least you have to provide the threshold frequency to eject out the electrons from the metal surface. And here the summary of the whole we have discussed. For a given photosensitive materials and the frequency of the incident radiation above the threshold frequency, the photocurrent is directly proportional to the intensity of the incident light. It depends upon the intensity. Photoelectric current will depend upon the intensity of the incident light. For a give next point, for a given photosensitive material and the frequency of the incident radiation, saturation current is found to be proportional to the intensity of the incident radiation, where as the stopping potential is independent upon the intensity. Stopping potential is independent upon the intensity that you are providing. It depends upon the kinetic energy of the incident radiation that you are providing. That will contribute to the kinetic energy. And for a given photosensitive material, there exists a minimum cut of frequency of the incident radiation. This is known as the threshold frequency. And the last point I want to point out that the photoelectric effect is a spontaneous phenomenon. It will not take the times to happen the things. If you are if you are providing the incident beam less than the threshold frequency, if you are regularly providing that, it doesn't mean that the electron after some time it will absorb absorb the energy and then uh, electron will eject out slowly. No, there is no chance, there is zero probability of happening that. So thank you for the listening.